So hello everyone. So last time we solved the surface tension problem using the pressure difference and the curvature of the system. Today we are going to solve this problem with an alternate way. We are going to use calculus and the force applied by the water surface on the walls, and we will going to see that how it going to create a equation in a 3 dimension to solve this problems in a very unique fashion. So let's try to solve this problem using a different concept. As we can see in this problem that this curvature has some mass, but we are not going to take the entire mass of the system. We are going to take a small element of the mass. The things that I am highlighting, you can see the force exerting on this wall, suppose that is F, by this mass element, which is x equal to L. So we can see, and we can see that this force having component in the x direction called F cos theta, and there is another component in the F sin theta along the wall. So the way we are going to solve is that we are going to see that which component is responsible for this elemental mass. Suppose we are going to take any dx element, and how we are going to distribute it over this entire 3D module so that we can get an equation. So the equation we are going to use is that the first one is along the y-axis, that is F sin theta is equal to mg, right? This is the equation number 1. The second equation is the force and the surface tension, so which is equivalent to the F force acting on the wall and the surface tension times the length, that is the depth of the plate. So we can see that this depth of the plate we can measure this as. So these being two equations. So the thing is that we are going to find this mass m over the entire volume, and for that we need to find the mass with respect to the volume. So density is equal to mass upon volume. So mass is equal to density times the volume over the entire length. So we are going to integrate from 0 to L to get the entire volume, and we are going to take the elemental mass. So that can be written as m equal to 0 to L rho times dx times of y multiplied by L or d, the entire depth. So this is the dm element that you are going to integrate over. So volume of the liquid chamber. So if we look into this system, we can take an element here, and we are going to take this element in 3 dimension because this is a cuboidal plane in which the entire liquid is kept, and this element can be assumed to be as a dx length. Okay. So to compute the mass over dx length of y distance, so this element, if I draw it again, you will see that this element is in a form of cuboidal shape where the length is dx along the y centimeter with a depth of d. So this element we are going to compute it over the entire length, and we are going to integrate this element so that we are going to find the volume over the entire length, and we will then able to compute the mass of the liquid channel. Okay. So this is dx times, because volume we know is length into breadth into height, so volume of a system is equal to L into B into H for a cuboidal system. So it is nothing but dx times, that is this element, dx times of y times of d, right? So the dm mass is calculated over the density times, that is rho, times the volume. So this volume is nothing but rho times of dx times of y times of d. So we are going to integrate it over 0 to, let's say, L. So this dm mass being computed over 0 to L length. So we can compute it 0 to m dm is equal to rho times of dx times of y times d over 0 to L, because x ranges, this dx element being ranging from 0 to L length, right? So all these small element will going to be joined and going to give you the shape of the entire curve in a 3 dimension. So if you see the f sine theta component here, we can see this, the mass component over this entire channel is balanced by f sine theta, which is equal to mg, right? So this was the first equation I told you that we are going to use. But second, we also know that force is equal to surface tension times the length. We are going to give this force equation with the help of F is equal to surface tension times the d length. So first we are going to solve this, and then we are going to put the value of surface tension time distance to solve the equation of the force. So putting the second equation in the first, we are going to see that S times, we are going to take that S surface tension as S times d sine theta, which is F, is equal to mg, and m we have computed that it is rho times of dx times of y into d. So we can just compute it here, 0 to L, rho times dx times y into d. This is the m that we have find out, and times of g. So we can just cancel out d and d, okay, and we are going to find that s sine theta is equal to this integral times of g. But we also know that if you differentiate it, so we can cancel this d term and we can differentiate it. So once we differentiate it, we can see that this integral sign will disappear, and we are just going to write this equation as rho times of dx times of y times of g is equal to s cos theta d theta, right? So rho times of dx times y times of g can be represented as s cos theta times d theta, and we can just represent it as rho times of y times of g as s cos theta d theta by dx. So we need to eliminate this d theta by dx from the equation. You can see that y equal to, we can give y as tan theta. Yeah, the slope of the equation is tan theta. So y is dy by dx. So we have given that dy by dx is equal to tan theta. So we can just use this to eliminate the theta here. So we can write this in the form of dy by dx, which equal to tan theta, and d square y by dx square is equal to sec square theta d theta by dx. So we can write this d theta by dx as 1 upon sec square theta d square y by dx square, and hence we get rid of the d theta by dx that we were using it here. So we can write this entire equation here. So s cos theta multiplied by 1 upon sec square theta d square y by dx square. So sec square theta, cos theta is 1 upon sec theta is 1 upon cos theta. So you can write it as s cos cube theta is equal to multiplied by d square y by dx square. This is same equation of curvature that we have computed in our last video. We have computed it directly, is equal to nothing but is equal to rho y times g. So we can easily compute this rho y g times divided by s is equal to cos cube theta multiplied by d square y by dx square. But we know that this theta is being very small, is nearly equal to 1 because cos of 0 is equal to 1. So a very small theta would compute this entire cos cube theta to a unitary value. So this is nothing but d square y by dx square is equal to rho times y times g by s, which is what we wanted to find out. And if you see the options, we can see that this is the second option that we have computed. So hence we have used the equation of force along the wall and the equation of surface tension to compute this problem in a very different way than we have solved in our previous video. So this is helpful to understand the very insight of the problem, that how calculus is also used to solve this problem. In previous video we have just used the equation of curve to solve this problem. So these are the two different approach you can use to solve a single problem. So both the approach actually helps you to understand different method to solve any problems. So thank you for watching. Keep learning.